everyone to the 2018 tutorial to help guide newer people to the software and to analysis at GlueX. We're already running a little bit late, so we'll go ahead and jump right in. Mark Ito is going to talk about the iFarm and GlueX environment, setting off the software stack. Thanks.
The room filled up. Okay, so this is the title is given to me. I'm not sure what it means. Environments, and it's mainly going to be on the environment, on your shell environment. Sorry, Simon. Back to your office. Okay, so a little bit of terminology, then about this. Quick word about the shells that we support here, BCSH and Bash. That whole slide. Environments, scenarios, beginner and even advanced, intermediate, advanced. Beginner is when you just want to use software that's already built and out there. You don't want to do any software development yourself. These are all existing stuff. Intermediate, you want to customize things for your particular interest. And advanced, you may be trying to create or debug old problems. Okay, and then I'll say I have one slide on data and computing resources, and then final slide on just links and how to get help. Okay, and so this is a tutorial, so you're supposed to be able to interrupt me, right? Right?
Mm-hmm.
We have time. Okay, we have time. Oh, shit. It's being recorded. Okay, so terminology. I realized that none of my talk depends on this terminology at all, but I felt that maybe it might be nice to go over it. This is pretty standard sort of terminology, but perhaps not universal, and throw these terms around oftentimes. I thought for beginners it might be nice to get people oriented. Okay, so reconstruction is the process by which we take our raw data coming off the detector and transform it into particles or particle-like things, clusters, or whatever. Take the raw hits, put them together. Simulation, often called Monte Carlo, is the world of make-believe. Fake events that look very much like real data. 3 steps in the simulation. Generation is creating the theoretical 4 vectors at the interaction. So this is where physics knowledge goes in. You have to have some kind of model for creating those particles. Detector simulation is the part where you take a particle. Okay, so generation BGGen is an example of that, which you may or may not have heard of. Detector simulation, you take these particles, swim them to the detector, create fake hits in the detector elements, and then that's what we call HDJ-NUT or HDJ4 in our terminology. And then you have to do a step. We do this as a separate step of adding detector resolution or smearing the hits, making the perfect energy deposited in just some ABC count, which is off by some amount randomly, just like the detector does. Okay, so resolution introduction. This is smearing. Okay, and then the other buzzword is analysis. So analysis typically starts with particles already, so it comes out of the reconstruction. Oh, the last thing I should say is after you go through this process of simulation, then you want to take this fake data and put it back into the reconstruction. Okay. So whether the source was fake data or real data, you end up with particles or particle-like objects, and you transform them into physics-relevant quantities like invariant mass, missing mass, whatever. So at this point, the particle sources are 2. One is rest files, which are the output, the reconstruction, or root trees, maybe generated during the reconstruction, but more likely some step after the rest files. So those are just kind of lists of kind of nomenclature. Okay. So the shells, very quickly, as I said, we support 2 shells, CCSH and bash. So other variations of this shell, of this type of shell, are the C shell. Bash comes from the born again shell. I mean, this is the born again shell. Comes from the born shell, which was the original Unixy type thing. If you use a C shell-like variation or a born shell-like variation, and it's not one of these, then kind of all bets are off. Things are really kind of specialized. I think these two. I mean, you can try it and mess around, maybe make it work. You're not guaranteed the results. Common convention is that if it has a .sh, that's bash. If it has a .csh in the name of the shell script, then it's tcsh. That's common, not universal. And then in this talk, everything's going to be bash. And I won't constantly tell you what the set-in version.
You use bash or C shell?
Okay, so the beginner scenario. This is, again, a run software already built without modifying anything. Okay, so as far as your environment is concerned, it's just this one line. Source, group all these software build scripts, GlueX, jlab.sh. Again, the bash variation. So the TC shell variation would be a .csh. Okay. And just to break this up, there's this directory, standard directory that I'll use more than once, and that's this group called these software build scripts. So if you define that to be build scripts, then this line, of course, turns this source build scripts GlueX. Okay, and that sets up everything. I'm going to kind of go backwards. You don't really know what that means, but we'll break that out as we go forward.
Mark, could you just say, is this if I'm logged into one of the farm machines, like iFarm, that where I would force that file and have this set up?
Yeah. The other thing I should say is this is very JLab specific, okay? Because group all D is a JLab type thing. So for definiteness, I'm going to use the JLab, and most people actually do a lot of the work here. If there's time at the end, I don't have a slide on this, but I can talk about reproducing this all D world on your own, Windows machine, kind of thing. Okay, but that's only if I have time and if I keep going sideways. So, but that's a good question. It's JLab specific. I really should have said that. Okay. All right. So this is for the default versions of the software. What does that mean? Okay, so we have version sets where we link together all the various packages that we put together. I'll show you that. I'm going to explode this out going backwards. And we actually have version numbers for the version sets. So this is in other words a meta version number. Okay, and so if I want to use 2.35, then here I'm going to define this directory, which is the distribution directory. Okay, and I do the same line: source build scripts GlueX and sh, and then name an XML file, which happens to be in this directory version 35jlab.xml. Okay, so I don't have to accept the default version. I can use any. I can use alternate combos of versions. Okay, so what are these version set files? Here I use 2.35. This is actually what 2.33 looks like. This is in fact the current default. Okay, the file itself. This is the file in $dist where $dist is defined as. Okay. What is it? XML file. Okay, so there's some throat clearing here. Beginning. G versions, the opening tag. /G versions, the closing tag. File name, state. Okay, then we have package. Each package has a name. These are your familiar names of packages. Janus and Recon, blah, blah, blah. And in this case, every package has a version along with it. And there you go. If you get one of these from somebody that you trust, then the statement from that person is saying that these versions will work together. Of course, not all versions of anything work with all versions of everything else, right? That's called version hell, right? There's a name for it. You can Google that. It's a thing. So these are not necessary, but they're sufficient. Okay. There are other combinations that will work. But if you trust the person from whom you receive this file, the statement is that these versions are in the domain of working combos. Okay. And and you notice that in SQLite there's year because this is just horrible. These guys make you put year in there. But the thing is, there's these dir tags. Okay, so the point is that if I build GlueX root analysis, okay, that depends on SimRecon. Way up here. This one here. That depends. So the point is that I may build GlueX root analysis version 0.2 many, many times, but using different SimRecon. SimRecon may march forward in time, while GlueX root analysis stays behind, stuck at 0.2. But every time I change a SimRecon, I'm now obligated to build a new GlueX root analysis. It depends on that. And so this dir tag doesn't say anything other than it's a tag on the directory name to distinguish it as being different from all the other dir tags. And I'm trying to give it a evocative name here. SR225 means that it was built against SimRecon 2.25, I think. Point is that you want to look at the SimRecon it was built against, it better be the one up here. And this is just a string of characters used to distinguish it. No meaning. You'll see that in the directory. So that's multiple version. That's to distinguish the various versions of version 0.2.
So I noticed that not all of your software has these tags. Does that mean that it's not important with other versions of software?
Yeah, that's right. For example, SimRecon is the one that changes the fastest for us, right? And so typically, when that goes forward and it's version 2.26, I don't have to distinguish version 2.26 from the other version 2.26, right? Because it's the first one. So the first one in any version typically has no dir tag. You won't see any annotation in the directory name. The directory will end in 2.26.0. And so the slower if it develops slowly and depends on something that develops faster, then you need the dir tags because its parent package is moving ahead and you have to distinguish it. You have to say which parent it belongs to. Okay, so that's the version font. And this is the default that you would get today if you do that one-liner and so on and so forth. Next is what? Okay, so what is that doing? That one line is setting up your environment. So it's defining a bunch of environment variables. Shell environment variables. So there's amp tools, like things, CVIO, beyond 4. This. Okay, so it's a lot to memorize. You want to do this by hand. Okay, that's the point. So this is the backwards thing. This is what we're trying to get at, in other words. The end. That's what this machinery is doing. And so the claim is that starting from this XML file, all of that stuff gets defined. Okay, with a few defaults that aren't specified here, but the richness and the detail of this thing is all captured. The point is that for any particular package, there's several environment variables that you can use. Libraries, binaries, da-da-da. Okay? And they need to be consistent with each other. But if you know it's version 2.25, that's enough to, and you're a JLab, that's enough to tell you what all those things do, and the scripts underneath will load that out, give you everything you need, allegedly. So I'm done now, and I'm not really busy. Okay, so there's a lot to do. So doing this by hand is tough. These are all new. All of these things were not present in the environment before that line, okay, or they were present added to by that line. Okay, so now after that's done, you can run the software. So type hdroot. This is our standard reconstruction program. I type that right at the command line. I don't have to search for where it is. It's in the path. Correct thing is in the path. This is, and you type out the usage message. It's really not very impressive. But if you think about how hard it was to get all this stuff right and get all the shared libraries, paths, and everything else, pity me. All so you can get the usage message. Okay, so I'm not going to say more about running the software than that. Okay, the intermediate scenario that I talked about is to perform, again, a custom data analysis. And we're talking about customizations of the type anticipated by the software system. In other words, known things that we know people want to do and things are set up for you to do. And really that is, I think, the meat of the rest of the tutorial. How to do your analysis, mainly analysis, and how to fix things up so that they go the way you want and do the things you want to do. So I'm not, and the environment set up for this is not in principle actually any different than the other steps. But this step, I mean, you see there'll be some coding involved, some minimal code. Okay, so the advanced scenario is you want to develop new features or debug old problems, as I said. So to do that, you need to create a custom version of the reconstruction that you can modify, recompile. Okay, so here's the complete session. You cd to some directory. I'm going to make a new directory custom. I cd into custom, and then I do this one command. So this is okay. So what does this do? You don't have to set up your environment actually before you execute this particular command. Okay, so what are we doing here? We start with the default version set. Again, the default version set for in 2.33 as of today. It defines local custom versions that you can modify of HDDS, SimRecon, HGeometry, GlueX root analysis. So this is the geometry package. This has our simulation and reconstruction binaries all packaged together. This is simulation package of the future. No, the future is now. And this is a analysis package. All manual. So these are the four things that you might want to put your hands on and change. Okay. Root. You're not going to go in there. I'm not going to do that. It's not. So these four, it builds them and it creates setup scripts to use after everything's done. Forgot to mention where those are, but anyway. So let's go.
Does it have code? Sorry, is there code there or code is in Git?
Code's in Git.
So you can't really change anything.
Once it's built, now you have a platform where you can go in and change. Okay, this is your SimRecon. This is how to make your SimRecon on the work disk. Okay.
Okay.
If you're a younger person, and you hadn't been doing this for years.
Okay.
I think
It comes from a
go ahead.
code.
Go ahead.
Just wondering where the code, in other words, usually I think of to get the code.
Right.
And then I build it.
Right.
Does this copy all the code or you don't have the code or where?
You'll see.
No.
What? One more minute. Okay, so I'm going to run this thing, one-liner that I told you, and it actually starts. This is the first few lines that come back out of the terminal. First thing it does is it makes an XML file for you. Okay, remember, this is your stuff. Okay, so and tells you what it's going to call it. Keys off the username. This is just a plain old copy of the default XML file, except SimRecon, for example, does not have a version. Okay. Instead, it has a home directory saying use the one that you find here, whatever that might be. Okay. And it happens to be in Scratch MarkEye Custom. Well, why was that? Because we ran this script in Scratch Custom. But it's an absolute path to the thing. So when you set up your environment, it'll point to that directory and do all the SimRecons off of that. So no version, but a home. HDDS, home. HTGN4, home. CCDB version. That means it's going to go back to the standard build that pre-existed. And so forth. Okay, now, the run is going on. This is coming out of your terminal, right? After you type that thing. And it says a git clone. -B, take the master branch. Into this directory, right? Oh, I've done this in front of you 3 or 4 times.
No, once it's done, I don't.
I had to pay him to act surprised like that. Oh! Okay.
This is magic.
Dude, that's why I don't. Okay, so clone. And checking out files, but ... Keep them going. Now it gets to this point. It CDs into this directory. Wow. Exactly the right directory.
It's magic.
It's unbelievable. scons install. Builds HDDS. Root GDMA. This is right, the standard thing. Then we go on. There's a ... I get to here. At this point, I've already cloned SimRecon. I didn't show that one, but it's the same thing. I'm installing. I'm building SimRecon. ... Now I get to later on in the SimRecon, it wants to build this. That's the first thing it builds. ... I'm going to keep going. Now I'm going to do HTGN4. Okay, and it does this. ... GlueX root analysis. Okay, so these, there were many hundreds of lines that are in the ... Builds the 4 packages. Okay, and then what I forgot to say is that in this directory custom, you will see a file that's called GlueXSetup.sh and GlueXSetup.csh. I think that's, and I should have put this in the slide, but let me just tell you that in custom, there will be 2 scripts, an sh and a csh. And if you source those, what does it do? It says do build scripts, with the XML file called custom markeye, Okay, so it'll point to the version file that was created at the beginning of the process. And you'll reproduce that environment. So Elton's right, it doesn't change anything, but this is setting the table so that you can change things. Okay, so data and computing resources. I didn't have time to do much on this, but I did. Okay, so there's this talk. These links work. If you click on them, the other workshop, which you heard about, I gave a whole talk on this. So you can look at that. CPU, disk, tape. You know what we have here. The numbers are kind of old in that presentation because it's. But anyway, it gives you a flavor. But there are two slides that I pulled out of here that I'm going to show. One is disk. So we have these flavors of disk at Jefferson. Okay. Work, MSS, cache, volatile. And this is jargon. What do we use work for? Work is for large files, personal builds, anything with event data, because those are big. It's work. It's called work call D. There's a home directory in there where you can create your own thing. Everyone should be able to write. If you're a member of the Hall D group, write to this disk. 120 terabytes, traditional grade. Flash MSS. This is a big array, okay, and this is a big directory tree full of little tiny files, and every one of those files represents a file on tape. Okay, so this is basically our representation of the tape library. Okay, so there's a one-to-one correspondence between the little tiny files in this directory tree and objects on tape. And so when you ask for a file from tape to the system, typically you ask for it by naming a itty-bitty file in the MSS tree. You know, some people go their whole lives without ever looking at one of those. In fact, there are probably people in this. But if you look in there, it's really boring, so it's okay. Okay, so that's a directory structure that you know about. Cache is a real directory. A lot to say about this. It's basically an image of MSS, but so that when you can pull files out of the tape library onto cache, and it goes into the same directory as that little tiny file /MSS. Only drop off MSS with /cache. And it goes two ways too. You can dump data into that. I'm not going to go into the whole thing, but this is where we keep most of our stuff that you think about as being tape. Think of it as a disk representation of the tape. And it's read-write. So when you write in there, actually you're writing, it'll eventually get written to tape. That's very vague, but a lot of questions off of that statement. Okay, the last thing is volatile. This is really just scratch. Okay, 175 terabytes is our reservation here. I did update these numbers. Volatile, we have 35 terabytes. We can go over these numbers, if there's space available in the partition as a whole. Okay, these are both clusters, so they're huge partitions. So this is temporary storage. As time goes on, files will automatically be deleted. So depending on how active the disk is, you gotta watch what the latency is, how long your file is going to live. How am I doing on time?
Way over.
Yeah. Okay. The last thing is we have an analysis wiki page here, offline software, oriented stuff page, JLab scientific computing, tape disks, other jobs, all that stuff is accessed here. I mean, the documents for that. Email lists, standard. This is our official offline software list. There's also a physics list, which has to do with physics and physics-related software issues. And I just want to highlight this one thing: GlueX software at googlegroups.com. This is the archive of that email list. This is where you go to ask questions. This is where you ask your stupid question, okay, without embarrassment, until, of course, someone flames you. But you know how these things are. The idea is a low threshold, of expertise to ask naive questions, and everyone sees it, and then, get people fighting with each other about the right answer.
Yeah.
The usual shit. Okay, and that's all I have.
Okay, questions for a coffee break, I guess. Next up, Alex Ostrajeslo will talk to us about plugins and reaction filter, the reaction filter.
Oh yeah, I didn't have time.
Yeah, thanks, Mark, for the introduction and thank you all for coming. I think it's not you shouldn't be too strict with it.
No, I don't.
Because everybody's here to learn
Well,
something.
then can I go talk about this?
Stay down.
All right. So I'll talk about plugins and reaction filter, and there's a versus. First item is very short, and then I will focus on the reaction filter. Now, Mark has introduced our GlueX reconstruction, analysis, and simulation software, which is called sim-recon. Soon, maybe it will be split into a simulation part and a recon part, but this is not the case right now. So I will still use the terminology of sim-recon. The executable has been, the main executable that we use has been introduced by Mark as well, hdroot, and usually the syntax is hdroot minus p and the key and then equals a value. So this can be many things, and this sim-recon is really driven by plugins. So you put a plugin in here, and then only this will launch all the processing. And if you just run it without any command lines, it won't do anything.
Can I ask a naive question? I've been reading about sim and recon being split.
Right.
But could you briefly state what is the role of sim versus recon?
So
and why would you, in principle, have the two things together, and why do you now want to split them?
Why do you have these things together?
Yeah, like,
I think
what
only
are
history can tell. The thing is, at the moment, it's a giant repository that contains not only our reconstruction software, but also Giant, also Giant 3, which is, or the coupling to Giant 3, then also the smearing part, the where you put in the resolution into the simulation part. Everything is in one repository. Now, as Mark said, the repository is evolving very quickly, but sometimes one part, like the reconstruction part, is evolving while the simulation part isn't, or is only evolving later. And to get around these discrepancies, we want to tear them apart and really have one branch that evolves in one direction and the other part that evolves in the other direction. Otherwise, it makes, especially simulation of older data, really hard because you have to update some parts of the repository, not others. Yeah. And at the moment, this is managed by the person here, and Sean in the corner, and he can sing you a song about the problems that you get with this.
I think you're trading one basket of problems for another. You split this, then I'm just talking off
Subject for another meeting.
of my head. Yeah.
No, let's get into this right now.
Duke it out.
Okay, so coming to the plugins, now they're in the repository. There are lots of different plugins available. Just look into it, and these should actually work as a link also. So you go to the GitHub webpage and you look at all the plugins. They're in different folders. Now, two important plugins. Monitoring this, it's a plugin that just creates lots of histograms, and usually it was always stated this should be run every time you run any other plugin, just to make sure that you have all the things and you can immediately look at the histograms. And then there's a second plugin that is important. It's called DanaRest, that produces actually the REST files from raw data. Raw data is the data we take from the experiment, and it's saved in GVIO format. Or from simulation, you can do the same thing. If you want to do reconstruction of simulation, you also use the DanaRest plugin. And the command looks like this: hdroot minus p, and the key is plugins. So minus p plugins equals, and then the plugin name, for example, monitoring hist, or with a comma, other plugin name. Now, this is all in a command line. but soon you will see that you will have too many command line arguments. So you can put them in the config file, which makes things much more easy. So you have just the command turns into hdroot --config equals config file and the file name here. And then you can put everything you ever want into the config file. And the syntax in the config file is a little bit different. You get rid of the -p and you get rid of the equal sign. So you basically just have key and value. So as an example, and key is in capital letters, so you have plugins and then monitoring his, comma, data as an example. Okay, this is how in one slide how to use SimRecon. Now the generic SimRecon plugin you can create with a command, and these commands, they are all in the paths that were introduced by Mark. So you just type it in the command line, make plugin, and you give it a name, which will make a plugin, a generic plugin. This can be used for monitoring, detector performance. But this is really not the focus of this presentation. As I said, there are already many plugins there, and if you really want to create a new plugin, you're probably already an expert. So the second thing, we have reaction plugins. This is a certain type of plugins that basically help you with producing a physics analysis, so a final state with particles. So it's an interface to the analysis library. And you make a plugin for a reaction. There's this command, make reaction plugin with a name. So here in the plugin, you can define reactions. You can make initial cuts. And it comes actually with a lot of example code already commented out. So you can just look. And the output of one of these reaction plugins is a standard analysis root tree that will hopefully be introduced in the next session. Sorry, Justin. So Paul Manzioni gave a large presentation about event selection in Jana during the work, during the last physics workshop, and he talks all about these things, which was actually the state 2 years ago. Now we have evolved the last 2 years, so the question is, do you even have to write in your own plugin? And the answer is probably not. There is one plugin, it's called Reaction Filter, and then that can do almost all reaction you can think of. So you probably don't even have to bother writing code. You just set it up with a command line argument or with a config file. That's why I introduced it before. So this really makes it easier to have consistency between all the analyses, and also we can generate these root trees centrally here, and everybody can use them. It doesn't even have to know what is in the code because they're all the same. So this reaction filter can set up every final state you can think of. You just have to use the particle ID numbers, which are defined in the particle type .h, which is also in SimRecon. It's a link in the presentation, and they're sort of the same as the GN PIDs. There are a couple of additions, but like if you're familiar with the GN PIDs, you will figure it out. So this is an example. You want to, for example, analyze the reaction gamma p goes to pi 0, pi plus, pi minus in the proton. The only thing is you have to do to specify the reaction like this. So it's the same thing, but with this GN particle IDs. So you have a 1 for a photon, a 14 for a proton, then you have 2 dashes in between for the error, and then you have a 7, an 8, and a 9, which is pi 0, pi plus, and pi minus, and then you have a 14 for the proton. Now, if you do that, you run reaction filter, and you have this line in your config file. This reaction will be printed in the command line in a more humanly readable format, so that you can check if all your numbers are correct. And then this number, reaction 1, is actually arbitrary. It's just that if you define more than one reaction, they shouldn't be the same. Now, again, Paul gave last fall in the collaboration meeting, he gave a big presentation about all the things he put in and everything you ever need to know about the reaction filter. I just focused on a few details here, which are maybe useful to put in one slide. Now, one convention that we just decided after Paul gave the presentation last fall is to use an order of particles in a specific, or use the particles in a specific order. This basically is irrelevant. You can, if you run your own reaction filter, you can do it whatever you want. You can put the particles in whatever order you want. But since we do these massive launches over the whole data centrally here, and maybe one person is looking at pi 0, pi plus, pi minus, and the other person is looking at pi plus, pi minus, pi 0, we don't want to create 2 times the same tree. So we decided to give the particles an order, and the logical thing is to give them numerical ordering. But since we're so used to having variance as like a recall, we decided to put the variance last. So for example, you have already seen it here, numerical order, so 7, 8, 9, and then 14 is the proton, which is the variant. It's pretty easy. Now, if you, for example, have an eta, which is 17, you don't want to have it 8, 9, 14, 17, because we're just so used to having the proton at last, so we decided to put it like this. But there's still numerical order, so 17 is behind the 9. Now, if you have decays, like decay of the eta here, or decays of the pi 0, they're defined by default in this folder, or in this file. Now, if you want to have a different, not the default decay, you have to specify it. And again, you can also specify it on the command line. For example, you don't want the, in this example here, pi 0, pi plus, pi minus, you don't want to have the pi 0 decaying into gamma gamma, like it's the default, and it's the biggest branching ratio, but you want it to decay into gamma e plus e minus. You just specified it here. So the decay is the same as the reaction itself. So you have a 7, which is the initial particle, 2 underscores, and then 1, 2, 3, which is coincidentally it's a gamma and E plus and an E minus.
So that will modify the reaction that you created.
That will modify only the reaction 1, right? Okay, then of course you can also have missing particles, and they're specified with a small m, and then the number. So for example, if you want to look at pi 0, pi plus, pi minus, and no proton, a missing proton, you specify it like this. Now it's important. For example, if you assume that there is a proton, it still tells the kinematic fit that the mass of the missing particle should be a proton. If it should be purely inclusive, so pi 0, pi plus, pi minus, and anything, you can use the 0, m0. So this is really
literally
nice.
on the command line, or
Sorry?
when you say you specify on the command line?
On the command line, or in this terminology in the config file. But you can do everything in the command line with minus p equal, but this gets very, very lengthy. That's why I decided to only show the examples from the config file.
Thank you.
Okay, there are some special options, and I don't want to go into detail here. So you can specify what type of kinematic fit you use, so no fit, or the default, which is P4 and vertex, but you can also use other fits. You can specify how many beam bunches on each side of the coincidence peak you want to save. The default is 1, so 1 on each side, 2 in total. There's a flag about the total number of extra charge track in the event. Here the default is 3. I did not even see a study yet how this affects. Then you can not constrain a mass of a particle in a kinematic fit with a capital M, and then also this unused hypothesis. Save additional information to the tree. And also the flags are put in the config file just like this. So reaction 1 flags, and then the different flags with underscores in between. And also those only, they're relevant for the reaction with the number reaction 1.
You
So-
expand briefly on what U1 means, save unused hypotheses. What does that mean?
Yeah, this is really something for experts. So it will.
I'll say something about it.
Okay, great. Okay,
Okay.
then I'll refer you to Justin. This is an example config file that I put into the software folder that we provided for this tutorial. It's on the group disk as well in JLab, and this is just an example. So how a config file for HD root can look like. Plugins is monitoring this that we should run every time, and then reaction filter, and then you want to tell HD root to run with both threads, maybe you don't have to, and then you have, for example, 5 different reactions here, and you basically do an analysis of 5 different reactions, and all you need is this. You don't need to write any code, you don't need to write anything, and this is where you want to read it. It's 2 gammas, and then pi plus pi minus, and then 3 pi n, and 3 pi zeros, and then k plus k minus. But of course, the possibilities are almost infinite, so you can put whatever reaction you want into this.
So are you saying that the root file that gets produced now will have just all of these things
It will produce 1 root file per reaction.
Okay, so it segregates the reactions into different root
one
files.
root tree per reaction.
But you can haul the whole thing up with this one config file.
Correct. Okay. Some word on the default cuts, because they are actually defined all in the analysis library. So they will be applied to all analysis, not only the ones that are done with the reaction filter, but basically all the analysis that use the analysis library, which means also the plugins that I showed at the beginning, the standard reaction plugin that you write on your own. And you think you know what you're doing, but basically the analysis library already does a lot of things for you. So there are a couple of these default cuts, and they're really applied to all analyses. For example, all neutral showers are bigger than 100 MeV. And then there's some timing cuts on PID. There's an energy loss cut on CDC, which really has to be revisited. We just read out. This is has to be worked on. There's some loose exclusivity cuts on the missing mass squared, or if you have a missing particle, then it's around the particle that is missing. That's why it's important sometimes to specify it. There's invariant mass cuts for decays. If you have a kinematic fit, it requires the kinematic fit to converge, and then all cuts that I mentioned before are reapplied on the kinematic fit quantity. If you want to know all the cuts, you just put this into your config file, and it will print all the cuts, hundreds of cuts that are mentioned.
You just lost me on the last step. What does it mean that all cuts are reapplied on the kinematic fit quantities?
Now, after the kinematic fit, you probably have more information about the timing of the track, it's mostly the timing of a track in a detector. It's probably better defined now because it uses all the information from the other tracks and fits it into a vertex. So then you can reapply these timing cuts on the kinematic fit quantity.
Things like DEX or momentum dependency. You better measure the momentum with the kinematic fit, and then you apply that momentum.
And so this is built in. This is just part of the flow of this first level analysis.
Right.
Does it mean it applies then exactly the same cuts again, or the narrower cuts?
Part of them are narrower after the kinematic fit. Some of them are the same. Maybe this is also something.
But I would think if going through the kinematic fit, when things are supposed to become better, things have a chance to go outside of the original cut, then the original cut
is
too narrow.
Yeah, that's true.
So you shouldn't have to apply that cut again.
Yeah, I think some of them they're already implemented in a way that they become narrow, but not all of them. This is relatively new and has not been studied in detail. Now we have these default cuts. Now you also can change them if you want. The problem is just it will change them for all channels. You cannot change it for one particular channel. If you're running more channels at the same time and you change a default cut, it will be applied to all channels. So here also the syntax can be found in the same presentation that I mentioned before. Just have one example here. For example, if you want to change the default cut on the pi0 invariant mass, so there's some, the syntax is not so nice, but it's this combo underscore invariant mass cut, and then there's a lower bound on the pi0, which is the 7 in PID numbers, and then the mass 0.1. And sort of similar to this, you can change around missing mass cuts and missing anything. Everything that is done by default almost can be changed if you really want it. Okay, so when do you actually have to write your own plugin? The only possibility actually, or the only way you want to write your own plugin is when you really want to have tighter cuts. You want to really cut on something specifically, but you want to run it with all the other plugins in addition, like in a launch. Then we cannot change it in the config file because it will change it for all the channels. So you will have to write your own plugin, which is not that hard because most of the example code is there, and then the default cuts are already applied, so you don't have to type them. They're already. And then, of course, if you want to do some other custom study, like tracking efficiencies, you probably have to write your own. Last thing, just some useful histograms that you get from the analysis library. You will get a histogram with all the events at the beginning, and then what every cut that is applied by default, and you see all the cuts that are applied by default for this analysis, pi 0, pi plus, pi minus, what they actually do, what they cut away. So you see the convergence of the kinematic field, it cuts away a little bit, and some PIDs. So every histogram and every cut action is registered here. Now you see the biggest drop is in the first column, and it just says has particle combos. This is where from the number of tracks and showers, the topology of the reaction is actually formed. Now there's another histogram that actually shows you what is done in this first step. It's called combo construction, num events survive. And this is exactly what happens in the first big drop here. So you see there are also a couple of things. And if you want to know what all these words mean, you will have to look into Paul's presentation. Yeah, I think that's everything I wanted to say. Now Justin will tell you what you can do with the root trees that are generated with the reaction filter.
Thank you. Yeah, so Justin Stevens will be talking about analysis trees and the deselector, which is the
quick question to Alex. I mean, in recent times there was a version 9 of the analysis, and then there was a version 12. Is that when you rerun this reaction filter on that long list of reactions?
Right. So what we have is basically just one long config file that has all the reactions that people requested, and then we just run it over the REST files from a particular launch.
Yeah, and the difference between the different launches is just improvements and calibrations and limits.
As long as they run on the same REST files, there will almost be no difference between the different launches. That's why we do not want to run the same analysis code twice over the same REST files, because there will be no difference. We just, once we have new REST files, like there's also versioning of the REST files, and there we are at version 2 at the moment. Once we have a version 3, really new reconstructed data, then we want to reprocess all the channels again.
So if you have a given version of the REST files, the different versions of the Dana plugin thing are, you're saying they're negligibly small, or
There should not be a difference if the code did not change.
Different sets of channels.
Yeah.
So if someone didn't put in the cascade decay mode they wanted in
different
version
sets
11.
of channels.
Version
Okay.
12, they asked for it, and we make it.
Okay, different sets of channels. All right.
So if you don't find the tree and you have some decay mode or whatever that you want to study, and you want it included in the analysis launch, you write Alex, and they'll bundle those up.
But we'll probably need one Passover where everyone will put their channels back in once we fix these cuts.
Yeah.
Because that affects it.
But then we rerun starting with the EDIO files.
No.
No?
No, the cuts are based on the REST level.
Okay,
One
they're
of
at the REST level.
The cuts Alex was talking about here, these PID cuts that are too tight.
Oh, okay.
Okay. About trees.
All right.
All right. So I'll talk about analysis trees and deselectors, and this is all built on this GlueX root analysis package that Paul Mattioni wrote. So I'm just plugging this. Okay, so what's in the tree? Alex told you about this reaction filter plugin that writes out one of the trees. So we're going to be looking at one specific reaction, which is pi 0, pi plus, pi minus, B4, and Alex talked about how this came about in the reaction filter before. But this is, if you open one of these files in a browser, this is the kind of output you see. So there's branches in there for event level type quantities. There's branches in there for combo level type quantities, and we'll talk about that in a bit. But if you want to just scan through and look what information is available, you can just click through the T browser. And this is an example of the beam form momentum energy. And if you just double click on it, it makes a plot of the beam energy distribution for this particular set of data. And there's a wiki page that has the gruesome, gory details about what's in all these branches, which is here that Paul maintained and updated. All right, so that's what's in the tree. But maybe rather than looking at individual pieces, I can kind of give the general overview of what's there. So we're looking at this reaction for the context of today's tutorial. Gamma P goes to pi plus, pi minus, pi 0 proton. And so in the tree, we'll have all the measured objects that go into this reconstructing this reaction. So there are the incoming D beam photon objects, the D charge track hypotheses for the 2 charged pions and the proton, and then the D neutral particle hypotheses. And for each one of the events that passes the cuts in the plugin, so an event that satisfied the criteria that Alex mentioned, there's one entry in the T tree. Okay? And if there is any of the tracks or showers, these neutral particle objects or beam photons are included in a combination of those objects that make the right final state we were looking for, any one of those tracks are included in the tree by default. Now, these unused tracks and showers that Reinhard was asking about, we don't store every track that was in the event by default in the root tree. We only store the ones that satisfy the criteria for this particular reaction we were trying to study. But if you want to keep all of the extra tracks and showers that were in the event, you can add this U1 tag in the reaction filter, and then even if there were 10 charged tracks, all of them will be stored in the root tree for every event, for each event. In this particular case, if only one combo was there, you only have 3 charged tracks in the standard. We do store some composite information about the unused tracks and showers. So if we were looking for this reaction and there were 4 charged particles, then we would store the sum of the extra energy from one of those extra tracks that didn't fit into the combo. And so we have some kind of aggregate information about the extra energy and extra tracks in the event that you can use at the analysis of the tree stage. So that's the event-wise information. Then we have the combos or combinations per event. And so these are for every event, if you had more than 3 charged particles, you can have more than one combination in one event. So if there were 5 charged particles, you could pair the pions in different ways and put it with a recoil proton, and you get lots of different possibilities for this final state. Most of these combos, these multiple combinations per event, actually come from the extra beam photons that we have coming in. So even if we only reconstruct pi plus, a pi minus, a pi 0, and a proton, you get one additional combo for every beam photon that satisfies your reaction criteria. And so we have a lot of these, what we call accidental beam photons, which are extra beam photons that weren't the real one that produced the reaction. And we'll talk about how you can remove those a little later. And then for each of these combos, because they all have a different beam photon or maybe a different final state particle, they all have different kinematic fit quantities. So all that's stored in this combo information per event. So there's kind of 2 levels. One is the event-wise level, and one is the combo-wise level in the tree. Okay, so how do you analyze this root tree? There is the old style in root. There's a generic root class called the T-selector. And if you open one of these trees produced by the reaction filter, you can use pure root code and say make selector, and it will write a class that can loop through that tree. And that's the one option. But it doesn't know anything about this GlueX format, which Paul spent a lot of time developing. And so instead of using this old style, most of us are using the so-called D-selector. So this is a class that inherits from the T-selector from root, but it provides access to the familiar JANA-type objects like D-charge track hypotheses and showers that we have in the regular reconstruction SimRecon. So this is a custom class, and it's for this GlueX formatted tree, and it has lots of built-in functions and histograms and cuts, and we'll look through a few examples of those. And the way you make a new D-selector, so a new set of example code for your reaction, is you call this function called make D-selector. And so this is the command line down here, so you run make D-selector, have some tree that has the reaction you're looking for. So this is the standard naming convention for one of the reactions that Alex specified in the reaction filter. You need to know what the name of the tree is. So inside this file, what's the name of that tree? And then the name of the code you want it to create. So in this case, it'll make a file named dselector_omega_3pi.c and .h. Right. And what the code made by this function will be specific to this T-tree. And so if you have a different T-tree, you'll need to run this make D-selector separately because the contents of the tree are different, and it'll create a different set of example code for you based on it. Okay, so once you have this D-selector, it has a name. Like I said, it's called dselector_megapi_3pi.c. If you want to run that, you can open this full T-tree file that we looked at in the T browser before. You need to load the library, which has all this code for the D-selector functions, and then you can just tell it to process that tree. And this is standard selector process function that root has inside of it, and this will loop through all of the events inside of your tree and do whatever is inside of this D-selector function. And we'll talk about the different functions that are inside there in a second. So this runs with a single thread. It's a single core processing all the events. This can take a little while. There's a nice addition that Paul put in, which uses a proof light manager, which allows you to run multi-threaded. So it kind of sets up several processes that process in parallel all the events inside of this tree. And so you do the same step of loading the library, but then you can give it this process tree function, which processes this tree. You have to know the name of the tree and the code you want to use to process it, but then this 2 here tells you how many cores you want to use in processing. So that allows you to go through the tree much faster. You can also aggregate many trees together in something called a T-chain. This is where you basically combine a bunch of root trees in real time, and you can process them all with one of these function calls. One note is there's a temptation that you can set up your process to use 8 cores, maybe more, on one of the interactive nodes. If everybody in this room did this, that would take down the interactive node pretty quickly. So be sure not to abuse these interactive iFarm nodes. And Alex is going to talk about batch submission, how you could launch this inside of a job on the farm, the way we want to be processing. Okay, and there's a wiki page here which has a lot of this example code inside of it, not for this specific reaction, but. All right, so I mentioned that there's a lot of built-in functions in this deselector. So I took this example deselector omega 3 pi and pulled out several of the functions that are included in there. At the end, I'll have a link to the exercises, which has this example code that you can look at, and that's where these all come from. But say you wanted to look at all the particle ID histograms, so time of flight, delta t, dEdx for all of your particles in your reaction. You would simply add this line to your deselector, and it's there by default, and it'll fill all those histograms for you when you process that data. Say you wanted to add a cut, so there are histogram actions and there are cut actions. Histogram actions just fill histograms, and cut actions actually remove events from the sample. You can specify a cut on the time of flight delta t, so PID delta t at 500 picoseconds in this case. And so this is a simple way of adding those kinds of tighter particle ID cuts in your deselector. You can make cuts, or you can look at the results of the kinematic fit, kinematic fit confidence levels, chi-square distributions, and make cuts on things like the kin-fit figure of merit. And the other nice feature here is that you can pretty easily make mass histograms. So you can say that my reaction has a list of particles inside of it. So in this case, we want to find an omega in the pi plus, pi minus, pi 0 channel. And so we can add those into this list and pass that to our histogram action. And it will fill a histogram of the invariant mass of these 3 particles in some range that we specify. Okay. So these are lists of some possible actions that are predefined that you can use by default.
Yeah, I have a question. So what's the significance of doing pushback rather than just telling it to make the histogram?
So the significance is that this is all done in the initialization function. So these are setting up the list of actions that you want it to process. And then inside the process function, it will actually call all of these actions for every event. This is the initialization setup, basically. Okay, and all of the list of these actions, additional histogram actions, cut actions you might want to try are on in GitHub in this deselector library, and there's a d-histogram action and a d-cut action .c.h, and those have the list of all possible actions you could apply here that are predefined. Okay, so let's look at one advanced type action that was developed by Alex Barnes. This one's kind of cool because it allows you to look at the effect of your of all the cuts except the one that you're interested in, let's say. So this is our 3-pion invariant mass after all of our cuts have been applied. So there's a few particle ID cuts and a I0 mass cut somewhere in here. And so there's a peak for the eta, the omega, and then some continuum background. This is our best event sample after all the cuts have been applied. You can then say, what if I didn't apply the time of flight particle ID cut? So that's this one here. Then I would get this distribution. So it's not so different. If I remove that cut, it doesn't have as much of an impact analysis. But what if I remove the kinematic fit figure of merit? So apply all the other cuts, PID cuts, but turn off the kinematic fit figure of merit cut, and we see the background goes up significantly. So this is one way of this analyze cut action allows you to basically test all of your cuts individually or separate from the other ones and try to factorize which ones are the most significant. Okay, this is pretty new. This is the first time I tried it.
Hold that just once, and it does that for all.
Yeah, so you set this up as a the same place you set up all these de-analysis actions. Set up another one that's called de-analysis cut action, and it goes through and finds the list of all previous cut actions, and then makes separate histograms for each one of them, pulling out that cut.
It's pretty powerful.
So it's kind of a nice new tool that we have to try out. And so if anybody else has ideas of new cut actions, new histogram actions they want to add, welcome to make your own additions to the library. And okay, the events surviving the actions, you can make by default, there's a histogram of the number of events you start with, so input of your events in the tree, and you can see how they sort of fall away as you start to apply different cuts. They're flat for the actions where you're just making a histogram, since there, and this is the number of events you're left with at the end. You can do the same thing for the number of particle combos. So you can see at the beginning in the input, most of the events have one or two combos, but there are some cases where an event has 20 combos in it. And as you get farther and farther along, you get down to where most of the events have 0 combos, but these are the guys you're interested in with one combination. There. Okay, what if the action for the variable you want to look at isn't in this list of actions that are provided? Well, you could add it. You could put in a new cut action or new histogram action, or you could define your own custom cuts or histograms in this process function. So you have access to everything in the tree inside of this function, and so you can write your own. And many of the variables have sort of standard access functions. So in this process function, there's some, the default code has functions to get the form momentum for all the particles in your reaction, for example. And there are separate access functions using these wrapper objects to go get something like a T object that's inside of the root tree by itself. And so there's all that's detailed in this, the wrappers that are defined in this selector library. So one example, let's say you want to do this tagger accidental subtraction that I mentioned. So by default, we store tagger photons for some extra RF bunches outside of the main signal peak. And so if we use this B4 tag in the reaction filter, that means we get 4 extra RF bunches on each side, which is plus or minus 18 nanoseconds. So the distribution for that looks something like this, where the signal peak at 0, this is tagger time minus RF time, where you measure the time of the tagger hit minus the RF time chosen by one of the tracks in the event. And you can calculate this delta t, and these are the signal events, and these are background or samples that approximate the background the signal peak. So you can use these out-of-time guys on the sides to subtract off the background. That looks something like this. So you can histogram that delta t function, and then you can subtract off or weight the events based on this delta t distribution. And in the exercise, there's some example code as to how to do that. So this is an important step that everyone should be doing at this point in our analysis. Let's say you want to take your T-trees that come from the reaction filter and then save a subset of the events so that you could use them later in AMP tools, like Elton will be telling us about later. You can do that with the deselector. If you remove some events inside of the process function, you can use this flag called setIsComboCut. So each event or each combo has a flag associated with it that says whether it was removed by one of your cuts or not. And so if you set this, then that combo will not exist throughout the rest of your analysis. And so if you do that, and then you can use, there's some built-in functions which allow you to write out the standard T tree. So if you just want to make a clone of the tree you have, but with a subset of events, you can use this set of code, which is included by default in the deselector. Basically, it loops over all of the combinations and checks if any of the combinations were cut, or if at least one combination succeeded, then you don't remove that event, and then you fill an output tree, which has all the information in it, but only for the sample of events that passed all of your selection criteria. There's another form of the tree that some people requested, which is called the flat tree. So in this case, it's not one entry per event, but one entry per combo. And so now the flat tree has more entries in it, but the tree is so-called flat, meaning that there's not multiple combos per entry anymore. And so there's a separate function called fill flat tree, which allows you to fill this for the active.
You have the example I had before. If you have the combo is cut, but there is one surviving combo, the event that you write out has only that combo in, or has the other combos in again?
I believe it has everything in it.
Everything in it.
But it has the flag set that the other combos were cut. So if you check that flag,
information is handed forward into that tree.
That's right. So all the combos are there, but if you check that flag in the next step, you'll only use the ones that passed your cut. Okay, and then writing out these new trees, you can also add custom branches to the output tree. And so there's, using the interface that's there, you can create a new branch. Let's say you wanted to save this beam delta T value into your tree for a future part of your analysis. You could write that into the tree that's output from. Okay, one advanced topic, because it's come up a few times in different meetings. If you constrain the intermediate masses, your reaction, you can tend to bias the reconstructed distribution. So when we look at this channel that has a pi 0, pi plus, pi minus in its final state, by default, this pi 0 mass is constrained in the kinematic fit. And that means that if you apply a tight kinematic fit cut, you will, by definition, get a histogram that peaks at the mass of the pi 0, how it's constructed. So this is an example with that mass constrained, and if you make a cut at greater than 10 to the minus 5, you get a nice pi 0 looking peak. If you do the same thing but use the option that Alex mentioned, which is you release the mass constraint on the pi 0, so now when you apply a kinematic fit cut, you're just conserving form momentum, vertex constraint. Then you don't, you still see a nice pi 0 structure, but you see some tails of the distribution out at larger values here, and that's your background. And so what you're missing by having this intermediate mass of the pi 0 constrained is an ability to assess the background. So essentially by making a hard cut here, even your background events will appear in your peak. So this is probably a subject for a future tutorial / how-to. What we'd really like to do is be able to use these events and do some kind of a sideband subtraction. So use the events on the tails here as a background subtraction, and that's something, if people have questions, we can talk about it, but that's something we should talk about. Okay. Right, so takeaway messages. What I would like you to remember about deselectors. If you have a question or you don't understand something about these predefined cuts or actions, please ask someone. Mark mentioned this GlueX software group. That's a great place to ask questions, no matter what character they have. Second one, always do tagger accidental subtraction. We talked about this earlier. We're getting to the stage where this is common and be part of everyone's analysis. And getting to this point about the background estimation, think early in your analysis about what background subtraction procedure you want to use. If you get into a situation where you didn't ask the tree that didn't have mass, or that had the mass constraint applied, then you're stuck waiting for those trees to be processed background. So yeah, have ask questions and find a meeting to show your results. This is the same place Alex mentioned, and in this session, there are examples of all the code I talked about that you can try, and there's a set of commands, so solutions that you should be able to execute and get the same results we saw. Yeah.
But if this is an issue so that we constrain the mass on the intermediate particle, why not want the filter right away to be gamma gamma pi plus pi minus? Not even define the pi zero as.
That's possible, and we have done that. The advantage to doing that is if you run the pi zero, by default, it puts some loose mass constraint here. So you reject things that are way away from the pi zero peak that you cutting down on disk space.
But does a cut do the cut without fitting?
Do the cut without constraining the mass. Yeah. But in principle, if you wanted to look at pi zero, pi plus pi minus, and eta pi plus pi minus, you could just run gamma gamma pi plus pi minus at both. So we kind of set it up this way to use the mass cut as a way of reducing the event size. But yeah.
Yeah, I mean, so maybe to expand on one thing that you said. So these root files are actually a pretty good size to copy either, to your laptop or your home instance, depending on the size of what you're working on. So, it's not like, we want to run over REST data and we want to generate these things in JLab, but, you can do this sort of analysis.
So, supposed to be coffee 5 minutes ago, but last but not least, in the first session, Alex will go back up and tell us about batch submission.
Yeah, while I set it up here, I just point you again to you all know the wiki page since you registered. There is a link to the group disk, and then soon we will also put all the folders from the different sessions also into a GlueX, to the GlueX workshop repository on GitHub. But just that you don't have to go to the group disk. And then in the last talk of the session, I want to talk about batch submission. Now, of course, this is very specific to JLab itself. Justin said we don't want to flood the interactive nodes, so use the much bigger farm resources that we have here. And similar to all the other talks, the tools are already there. You don't really have to define or invent a wheel here. A short overview that I stole from Sean 2 years ago. The user interacts. He wants to interact with the batch farm and also the tape library and the file servers and everything. And there's a program or a framework that's called Swift that basically does everything for you. There is, especially the older users will still know, the system that actually does handle the batch jobs on the farm. It's called Augur. But nowadays, Swift does everything for you. So you will only see the word Augur sometimes in some error messages, but nobody has to handle Augur itself nowadays. That's why I will not even mention it. I'll just have it here on the overview. So Swift is the program we use to do workflow management here at JLab. And this is from the website. There's a SciComp website, scientific computing website about Swift. It will work tirelessly on your behalf so that you don't have to do it. And to make good use of the computing farm, which means it efficiently handles I/O input/output with the tape library. It does all the bookkeeping of the different jobs. It gives you a list of errors It makes it easy for you to resubmit jobs. At the moment, there is even a possibility to handle job dependencies, but I will not go into detail here. There is some documentation by the author of Swift, Chris Lario, who gave a presentation in one of our collaboration meetings a year ago or so, and there he mentioned all the really new features and advanced user features that he implemented recently. In the future, they even plan to use the same software, the same workflow management tool, Swift, to not only send jobs to the farm that we have here, but even offsite. So to NERSC, which is a farm at Berkeley, and then Open Science Grid, which is the grid here. So just in the future, maybe at some point we're in a stage where we can use Swift and just send the jobs to wherever we want. At the moment, it's just sending jobs to the JLab farm. Now, there's a list of useful commands. Now, the first command, of course, is always Swift help. This will print usage instructions. And it also works with all the other commands that are listed here. So if you do Swift and an additional command and help, it will go more into detail about this command. Second one, which is really important, Swift list, will shows all your workflow, everything you have ever submitted. So if you have never worked with a batch farm before and you type Swift list, you won't see anything. But as soon as you create a workflow, it will show up here in the list. It takes a minute or so until it shows up, but it shows up there. And then so the usual mode of actions, you create a workflow and then you add jobs to the workflow. Now this is actually has really, really many command line options that I don't want to go into detail. This should be done with a script, and of course these scripts already exist, and I will mostly focus on these scripts. And then once you created the workflow and filled it with jobs, you run it, and then you can always check with Swift list what is it doing, and if some jobs didn't work, you can probably retry them. So retry the problem jobs here. Possible problems are Swift user non-zero. This is mostly your problem. So it means user. So user is you, and that the output of the process is non-zero. That means it probably crashed or there's a problem with your program. So you have to fix it. Check the logs or something. There are other problems like auger failed, Swift error, Swift auger unknown. This happens sometimes, and it's just random. It's a problem with the farm mostly, so just retry. And then there's a third possible problem, which is like timeout or over R limit, which is RAM. So here you check your resources when you submit jobs to the farm. Maybe you said the job should only take 1 hour, but it took 2, and then it timed out, or it used more RAM that you allocated to the job. So here you really have to check your resources. And then to delete the workflow, this is the command. Just cancel the workflow. If you really want to get rid of it, this one is. Okay, this is not an extensive list, but if you want to have all the lists of the commands, just type Swift help. Or if you want to know more about the individual commands, try Swift and the command and then help. Okay, one word about scientific computing, because this is, especially the website that they provide now, is really, really useful. I use it all the time. So it has a lot of information there. It has information about the individual nodes. So every column here is actually one computing node, which has a number of job slots, which are sort of number of threads that you can allocate in. You can see some of them, they have 24, some of them they have 72 threads open, and then if it's blue, it's actually used. So you can really see what's the status of the farm right now, and this is a picture where it's pretty full, but sometimes it's really empty, everything is green. Then you should really use that and submit jobs. You can also get information about usage, about the batch jobs, about the file system, about tape library, about file system here. A lot of information is on this webpage. One additional thing, there's a little box here on the right which says user. You just put your username there, which I did for an example, my username, and you get more detailed information about your own jobs. So for example, on the job, you click here on jobs, you see what are the different users, but yours is highlighted, and then you can always click and get more information on this. And then also if you click on Swift here, you will find only your workflows, and then you can check what's happening there. So it's really, really very useful, this web page. And it just has been updated like a year, less than a year ago, I think. It wasn't like this when we had the last tutorial. Now, okay, main part of the talk, the scripts that we have to submit jobs to the farm. They can all be found in this Subversion repository with this link. And these are links that you can click on and even look at it in the web browser. It's a really easy to use framework, but it's also used for the official production. So even the REST production, massive launches that run for a month or so, they use the same software. And then also the analysis launches that we do here over REST files, they also use the same scripts. And it can also be used even to run your deselector. Run your own deselector over analysis trees, use the same scripts. And since we still use it for the official production, it's also supported, which is good. It contains mainly 3 files, which is a Python script, Python program that submits jobs to workflow. There's a script.sh, which is a bash script that is actually the program that is running on the node, handles I/O and runs the farm node on the node. And there's a config file. And this config file basically steered everything else. It's the only thing that you as a user have to touch. You don't even have to look into the Python scripts or the bash scripts here. So how you submit jobs to the farm, you just run this launch.py with a config file, and then these are the run numbers. So you say run number X to run number 1. Then you will see all the jobs that are registered for your workflow. Pretty easy. So the only user modification you need is a config file, and that's why I will show you again one of the config files. And there, again, can be found also in the session folder. So this is a typical config file to run SimRecon on the farm. Doesn't matter if it is REST production, so it's a DanoREST plugin, or if it's a reaction filter or anything else. Typical config file. Everything is nicely commented here. There's some job accounting, so the project is GlueX, the track is analysis in this case. This can be reconstruction analysis or simulation, and this is just how it counts towards our usage of the farm. And then the OS you want. Most of the nodes nowadays are CentOS 7. Probably just use that. The resources of the farm that you need for your job, so the number of cores you want, the disk size, the RAM, and the time limit, and then some things dependent on your job you want. So the name of the workflow should be specified here. Now there's a system that you can use to replace something. For example, if the run period is 2017-01 and you need it in several places within the script, you can just define it and call it here. This is not, as it said here, it's not needed. It's just nice to use it like this. And then a couple of things, and here I reference all the other sessions that we had today. So the environment file you want is exactly the environment file you will find in session 1A. The script file is the one that I just mentioned before. Script that actually runs the file, the job. there's an RCDB query because you say you want to run these runs, but maybe you don't want to. Not so important. And then you want, since this is a SimRecon job, you want to specify a JANA analysis config file. Okay, you have an input directory and an output directory. And then there's one additional information, which are the cache pin days. This is just if your output directory is on the cache disk, and pin it so that it doesn't disappear for a number of days. But it's only effective if the out gear large on the cache disk. And this is done in a way so that you can, for example, write the log files to another folder where you don't write the big file. In my example, it's the same. Okay, so I provided this config file already. If you want to change it, please do. But I tried it with everything that is here in the folder, and it should just work out of the box. So what you do, you set up a workflow like this, and this workflow should match exactly the one you have here. So if you replace run period and version here with these numbers, you get exactly this number, and this has to match. Then you register the jobs. Just type this launch jobs analysis config, and then the run range. Now in this, there is an additional possibility to not run the entire runs, but only the first 5 files of these runs. This is optional. As an example, put the command, the syntax here. Then once you execute this, you will see many jobs will be registered with this workflow. After this is done, you can run it, and then you can periodically check what is it doing. You can use Swift list, you can use the web page, you can check what's going on in the output folder. Now, I tested this, and it works. But of course, if everybody in the room tests it, they will all write to the same output directory, and there will be some interference, and your jobs will maybe crash. So to avoid interference, just copy the config file if you want to try it, and put the output directories to somewhere else, and then it should just work like this. Okay, and now this was for SimRecon. If you want to run a deselector, like Justin just introduced, it's the same program. It's the same script that does it. So you can also do this. The config file looks a little bit different because there's several things you don't need, like the JANA config. But there is a few things you need now. So it's they have this block called root config, which actually shows you you need a script that runs the deselector, but you don't have to touch it. It's already there. You have to have a tree name. I use the same as Justin before. And then I actually used Justin's deselector that he created in the session before. So this is the link to the deselector. And everything is the same, else is the same. You have some input, which should be the tree you want to look at, and some output. Yeah, that's it. So you do the same thing. You create a workflow, you register the job, and you run it. You periodically check, and that's already done. And again, if you want to try it, and just copy the config file and edit the output directory. Otherwise, it will all write to the same, which is volatile. Yeah, if there are no more questions, I just hope that I'll see very busy farm in the next weeks, where everybody's submitting jobs and doesn't stick to the interactive nodes anymore. Now, important questions now. What about the coffee? Don't have coffee.
I failed on
Oh,
okay. But we can have a short like party break, and then reconvene in, I don't know.
5:20 is the official second session start time, but
5:30.
5:30.
5:30
sounds about right.
Okay.
Georg has a question.
Yes.
When I just try the Swift help, I get an error that I need a scientific computing certificate.
then you need a scientific.
Oh yeah, we did that. Yeah, we had that issue, I think. Campus. Very familiar.
Okay. Other questions?
15 minutes. Okay.
No, it's these are